Hey everyone, my name is Akil Nastala. I'm currently an engineer for YouTube in San Bruno, California. During my last year and a half at MIT, I had the fortune of working with Professor John Gutag on a thesis in basketball analytics. We applied modern machine learning techniques to newly available player tracking data from the NBA to gain a better understanding of patterns of player movement in the National Basketball Association. We started with the premise that great player movement is paramount to success in the NBA and broke this down into the following 3 steps. Better patterns of movement on offense lead to higher quality shots. Consistently taking higher quality shots leads to a better overall offensive strategy, and a consistently better offensive strategy over the course of many games or over the course of a season leads to more wins. There's a wealth of big data available on NBA player movement. We were specifically concerned with spatial court coverage and not vertical player movement, such as jumping. We use this data to develop a set of tools that make it easier to ask and answer questions about how players move on offense. Before we began work on our framework, we identified a few types of questions that we would like our framework to be able to answer efficiently and comprehensively. How did Paul George's style of play change after he injured his knee in 2014? Which possessions from the 2015 playoffs involved a dribble penetration and a kickout in which a three-pointer was made? Which players have the most similar patterns of movement to LeBron James, and how can we quantify movement similarity? Sorry for the short clips, but on the left, we see Paul George before his knee injury in 2014, driving to the left. And on the right, we see Paul George a full season removed from his knee injury, driving to the right. While these are specific instances of these plays, this begs the bigger question. How did Paul George change his style of play after his knee injury? And if so, how? We used our framework to answer this question and arrived at the following results. We saw that overall movement in the right half of the court increased from just under 14% of his movements to nearly 45%, whereas movement in the left half of the court decreased from over 50% of Paul George's movements to just 29%. Furthermore, we saw that these increases and decreases were consistent in different areas of the court, such as the right wing, the right low post, and the right sideline. Now let's get into how we use our framework to answer these types of questions. So what data do we have at our disposal? We had SportVU time series data as well as SportVU event data. There are 6 cameras in every NBA arena that track player and ball movement at 25 frames per second. Furthermore, they also record the location and timestamp for various basketball events, such as rebounds, made and missed field goals and free throws, rebounds, turnovers, fouls, and so forth. We have this data for the 3 NBA seasons from 2013 to 2016. Since then, SportVU has been acquired by Second Spectrum. Our ultimate objective is to build a set of analysis tools that can support a wide range of questions on how players move. We broke this scope down into 2 specific applications, the Similar Possessions Finder and the Movement Profile Builder. The Similar Possessions Finder should be able to support efficient search for similar possessions by player movement. For example, it should be able to efficiently and quickly answered a search which possessions from the 2015 playoffs involved a dribble penetration and a kickout in which a three-pointer was made. The movement profile builder should be able to summarize aggregate player movement over the course of many games. It should be able to answer questions such as, how did Paul George's style of play change after his knee injury, and which players have the most similar patterns of movement to LeBron James? Let's take the first question, for example. Which possessions from the 2015 playoffs involved a dribble penetration and a kick out in which someone made a three-pointer? Right now, I believe film analysts could spend many hours watching raw video footage in order to answer such questions. We realized early on in our research that it is also too computationally expensive to directly search the Sport VU time series data in an attempt to answer such questions. This led us to the realization that we want to represent every offensive possession in a common fixed input space that is easily searchable, such as a set of images. A trajectory image is a 64 by 64 image that captures directionless player movement after the ball crosses half court. We build each trajectory image by first segmenting the offensive half of the basketball court into a 64 by 64 grid. We then map each offensive player's trajectory onto that image using the Sport VU time series data. Those 5 images there are from a single Warriors offensive possession from Game 7 of the 2016 NBA Finals. Since we only map each possession from the time the ball crosses half court to the end of the possession, we observed that Klay Thompson, Harrison Barnes, and Andre Iguodala have movements that begin after half court, whereas Draymond Green and Stephen Curry have movements that start at the half court line. While this is a good start, we still realize that it is simply too computationally expensive to search for similar movements amongst trajectory images. The reason being that in order to compare 2 images, you need to compare thousands of individual pixels, and comparing and doing this search for all 3 million images in our data set is simply too computationally expensive. We're seeking a representation that can efficiently identify those top set of movements as similar and the bottom set of movements as dissimilar. Currently, the Euclidean distance between the top set of movements and the bottom set of movements is 0, even though the top set of movements is similar and the bottom set are completely different movements. We turned to deep learning to look for a solution. On this slide, you can see our deep learning architecture. We used a convolutional autoencoder network. Every trajectory image in our data set, all 3 million images, were put through a series of encoding layers and reduced to a 32-dimensional embedding. The original image was then reconstructed from this low-dimensional representation. We trained our network to minimize the loss between the original and the reconstructed image. Training a single model for all movements in our database lets us learn a low-dimensional representation for each movement in the context of all movements. As a quick recap of what we've done so far, we began with raw Sport VU time series data. We decided to represent this data as a set of 5 images for every possession on offense. We still realized that this set of images was too expensive to search directly, which motivated a deep learning solution. At this point, we put all 3 million images through a convolutional autoencoder architecture to generate a 32-dimensional floating point vector for every movement on offense. We call this 32-dimensional vector a trajectory embedding. Each trajectory embedding captures the spatial patterns of the image that it is generated from, such as the start and end points, potential screen actions, and court coverage. We're very interested in seeing if trajectory embeddings can be used to find similar movements on offense in an efficient manner. To determine if this is possible, we took an input trajectory image, which you can see in the first row on the figure to the right. We generated the embedding for that image using our trained model, and then found that embedding's 10 nearest neighbors in embedding space by Euclidean distance. We then retrieved the original image for each of those embeddings, which you can see in the second and third rows of that figure. The movements in those 10 images are remarkably similar to the movements captured by the original trajectory image. Repeating this procedure over thousands of examples convinced us that trajectory embeddings can be used to efficiently search for similar movements on offense. This result led to the Similar Possessions Finder, which is a database of basketball possessions. Each row in this database corresponds to one player's movement over a single possession. The row includes the movement's trajectory embedding, as well as useful possession metadata, such as the game ID, the quarter, the game clock, the player ID, and so forth. While each row in our database has a unique primary key, the 5 rows that comprise a single possession share the same possession ID. Furthermore, the trajectory embeddings are stored in a data structure known as a k-dimensional tree, which facilitates efficient nearest neighbor search amongst higher dimensional data. Although the trajectory embedding itself is a low-dimensional representation of the original trajectory image, because it is 32 dimensions, it is considered higher dimensional data, which makes it apt for a k-dimensional tree. So how does the Similar Possessions Finder work? Let's walk through a sample query. Suppose we want to find all possessions from the 2016 playoffs in which Kevin Love posted up on the left block while sharing the court with LeBron James and Tristan Thompson. The Similar Possessions Finder first finds a single instance of Love posting up on the left block, which we refer to as the input row. It next searches the k-dimensional tree using this input row's trajectory embedding and retrieves all embeddings which fall within a certain similarity threshold. It then filters this set of embeddings to match the input query parameters, which in this case are only possessions from the 2016 playoffs in which Kevin Love shared the floor with LeBron James and Tristan Thompson. Finally, it returns the result as a list of game ID, quarter, and game clock. Returning the results in this format makes it very easy to pull out the specific plays in which, from the 2016 playoffs, in which Kevin Love posted up on the left block while sharing the court with LeBron James and Tristan Thompson. We augmented our specific instance of the Similar Possessions Finder with SportVU event metadata in order to support even richer queries. In addition to the trajectory embedding and essential possession metadata, each row also contains information about what else happened in the possession. Did the player give or receive an assist? Did the player get a rebound? How many passes were in the possession? What's the current score? and what fraction of the entire possession did the player handle the ball, and much more. Augmenting the similar possessions finder with this event metadata lets us support very rich queries, for which we give two examples on the screen. We can find all possessions from the 2015-2016 season, in which Russell Westbrook handles the ball for 80% of the time and passes it to Kevin Durant for a three-pointer. We can find all Spurs possessions from the 2015 playoffs, in which the Spurs passed the ball at least 5 times and a player converted a three-pointer from the left corner, and much, much more. Although the similar possessions finder can be used to answer a wide range of questions, it is still not entirely suitable to ask two of the questions that we posed earlier. How did Paul George's style of play change after his 2014 knee injury, and which players have the most similar patterns of movement to LeBron James? We realized that we can answer these questions and more by grouping together or clustering visually similar trajectory images. We can accomplish this by running a clustering algorithm over all 3 million trajectory embeddings in our data set. We decided to use k-means clustering as it is quite suitable for large data sets. We found that using 20 clusters yielded a more interpretable set of results than higher or lower values of k. The central element of each resulting cluster is called the medioid and can be used as a representative element for the type of movement that cluster represents. You can see the 20 medioids that we generated from k-means in the figure on the left, as well as a description for the medioids on the right. We found that there were 7 sets of reflective clusters, where one cluster represented a movement in the left half of the court, and another cluster represented a movement in the right half of the court. For example, cluster 7 and cluster 8 represent what look like potential screen actions or movements above the right and left wing, respectively. Cluster 13 and cluster 14 represent what look like movements along each sideline to that three-point corner. We additionally found that there were 5 clusters that equally span both the left and right half of the court. For example, cluster 15 represents a movement that looks like a run along the baseline, and cluster 18 represents what looks like a lateral movement in the high post. A cluster profile is a 20-dimensional vector that represents how frequently a given player's movements or trajectory images fall into each of the 20 clusters from k-means. For example, during the 2015-2016 season, over 20% of Andre Drummond's movements fell into cluster 1, which is a movement from the top of the key to the right block. This is a movement that's characteristic among big men in the NBA, and especially for Andre Drummond, since he prefers his right side. During the same season, we found that over 20% of Klay Thompson's clusters fell into clusters 13 and 14, which are movements along either sideline to the three-point corners. These movements are characteristic for players who are three-point threats and spend more time on the perimeter in order to space the floor. A cluster profile is essentially a summary of a player's aggregate movements over the course of many possessions or many games. We use this result to develop a tool called the Cluster Profile Builder that can generate a cluster profile from any input set of players and any input set of possessions. The set of players can be an individual player, an entire team, a given position, and so forth. And the set of possessions can be from a single game, a set of games, a range of dates, or even an entire season. We used this tool to conduct several case studies, and one of them is shown here. We went into a deep dive to examine how Kevin Love's movements changed after he was traded to the Cavaliers in 2014. Kevin Love went from being the primary option with the Minnesota Timberwolves to being the third option with the Cleveland Cavaliers behind LeBron James and Kyrie Irving. The blue vertical lines in the graph represent Kevin Love's movements when he was in his final season with the Timberwolves, and the orange and gray vertical lines represent his movements during his first 2 seasons with the Cavaliers. Right away, we observed that Kevin Love spent less time in the interior, movements represented by clusters 1 through 6, and more time on the perimeter, movements represented by clusters 7 through 14. This confirms many analysts' belief that Love became more of a perimeter threat during his time with the Cavaliers. However, what the cluster profile offers is an ability to break down where exactly his movements increased and decreased, and by how much. The trajectory embedding is an instrument that can be used to efficiently and comprehensively analyze individual player movement on a possession-by-possession basis. We use this instrument to develop a few set of tools to answer some interesting questions: the Similar Possessions Finder and the Cluster Profile Builder. We believe that these tools and more can be very useful for coaching and team personnel in the National Basketball Association. We would like to thank the Boston Celtics and the National Basketball Association for providing us with Sport VU time series and event data from 2013 to 2016. I would also like to personally thank my research advisor and co-author, John Gutag, who could unfortunately not be present today. And I would also like to thank my lab mate, Joel Brooks. Thank you very much.
We'll open up for questions, so please raise your hand.
So can we use the train trajectory embeddings for like other researches? Is it on GitHub or somewhere?
It's currently not open sourced.
In order to obtain the trajectory images that you eventually fed through the convolutional network, how did you actually make those mappings? Or were the actual possession images or possession video the one that you were feeding through the convolutional network?
So we first started with the raw Sport VU time series data, which at 25 frames a second, we had each player's XY coordinates on the court. And then we segmented each half of the basketball court into a 64 by 64 image. Each pixel corresponds to a range of coordinates from the time series data. And so it just became a simple mapping at that point.
We have time for one last question.
Which player is most similar to LeBron James?
You know, it was some random player, man. But I don't remember off the top of my head, but however, what we would use to answer that question is we would generate a cluster profile for each player and then find the Euclidean distance between each pair of cluster profiles. And then whatever pair of players has the lowest Euclidean distance is the most similar to LeBron James, yeah.
Unfortunately, we're out of time.
I think it was like Spencer Dinwiddie or something. It was something random.
Let's everyone give a hand to Akil.